Hello, and welcome to Astronomy 100. In this segment, we're going to take the rules that govern the behavior of atoms as described in the previous segment, and we're going to use those rules to show you how the creation of an absorption line spectrum is produced, and of course the creation of an emission line spectrum is produced, and we'll see how they compare to each other. So let's go to our first slide. If you recall from the previous segment, what we find is that there are three possibilities that can happen in nature. The continuous spectrum, where there are no lines, absorption line spectrum, where there are dark lines against a colorful background, and then of course an emission line spectrum where you have colorful lines against a dark background. Now the internal workings of an atom is going to govern how this is going to be produced for one of the other choices here. So let's take a look here. Let's start off with the creation of an absorption line spectrum. If you recall from a previous segment, we talked about how to create an absorption line spectrum, you need a source of continuous light, and so in this case we're going to use the incandescent light bulb as the source. And if you recall, an incandescent light bulb has a very hot piece of metal inside of it, and Kirchhoff's law for continuous spectrum is one where if you have a hot solid, it will produce all of the colors of the rainbow, or a continuous spectrum of white light. So this incandescent light bulb is producing every color of the visible spectrum. As the light goes off in all directions, we're going to follow it in the direction of your eye. Your eye may not necessarily be blue, but let's just say that this is your eye, and you're looking at the light coming from this incandescent light bulb. Now we're going to introduce a cloud of hydrogen gas, and even though we can't see them because they're very small, this cloud is composed of countless numbers of hydrogen atoms. And to make life a little bit easier, we're going to take one of those hydrogen atoms and we're going to make it big enough for us to see. So here is the nucleus of the atom with the one proton. Remember that having one proton makes it element number one, which is hydrogen. And then surrounding the nucleus are the orbital levels that hydrogen allows for its electron. So the electron can exist in level 1, 2, 3, and it's a little hard to see, but there's level 4. These are the 4 orbital levels that the electron is allowed to be in. For this particular example, the electron is already in level 2. And we'll find out why eventually. So this electron is orbiting the nucleus in level number 2, and the light from the incandescent light bulb is going to pass through the cloud of gas to your eye. If you remember from Kirchhoff's law that an absorption line spectrum is produced when you have a cool, transparent gas in front of a source of continuous light. So we've met all of the conditions for Kirchhoff's law. Now let's start with yellow. So let's say that this light bulb, which produces every single color, has photons of yellow light that will come from this incandescent light bulb. The yellow light will pass through the gas, and let's say that this yellow light encounters the atom with the electron already on level 2. Now what I want you to notice is the yellow light goes through the cloud, comes out the cloud, and it makes it to your eye. In other words, this atom has ignored the color yellow. The yellow goes through, continues through, is ignored by the atom, and you get to see yellow. Now, on the other hand, let's imagine the color red coming from the light bulb. So this is photons of red color that are going through the cloud of gas. But notice how the photons that are red encounter the atom, but the atom does not ignore red in this instance. Instead, the atom will take the red photons, absorb the red photons, and cause the electron to jump an energy level. So notice the red came in, the red was absorbed, and the electron jumped to a higher energy level. And the red, consequently, never makes it to your eye. So in reality, certain colors are ignored and certain colors are absorbed. And so what we end up having, it's summarized on the bottom here, for the element hydrogen, the color red, it corresponds to a jump that the hydrogen is allowed to make. Remember, the atom is only going to allow its electron to jump from one level that's allowed to another level that is also allowed. And red happens to be the color that will force the electron to go from level 2 up to level 3. It gains energy by taking in the photon. So essentially, that particular shade of red will always get absorbed by the atoms with their electrons, and it never makes it to your eye, causing a dark line. So this shade of red is never allowed to make it through the cloud because all of the hydrogen atoms will take that red photon and force the electron to jump up to a higher energy level. So that's why we call it an absorption line, because that color of red is absorbed out of the visible spectrum. However, the yellow that we saw in the previous section, or the previous slide I should say, the yellow that was ignored by the atom, this is yellow that corresponds to a jump that is not allowed. It's trying, the color yellow is trying to make the electron jump from level 2 to level 3.5. But there is no level 3.5, it's not allowed, so the electron is not going to do what it's not allowed to do. So the yellow gets ignored, and of course if the yellow gets ignored, it makes it through the cloud, and you get to see yellow. So when you look at an absorption line spectrum, the colors that you see come from the light bulb, and those are the colors that the atom can't use. Those are all photons of energies that the atom can't do anything with, so those colors make it through. But the colors that get removed are photons that have energies that will force the electron to do something it's allowed to do. And so in this case, the red is always the jump from level 2 to level 3 inside of a hydrogen atom. So you will always, for hydrogen, always see this shade of red missing. This shade of blue that is missing was the jump that some of the hydrogen atoms made by making the electron go from level 2 all the way to level 4, skipping 3. So in other words, the blue photon came in, the electron absorbed it, jumped from 2 directly to 4, and therefore that blue photon doesn't make it through. This shade of violet that's missing is the jump from 2 to 5. And then this is 2 to 6, and this is 2 to 7. So the electron jumped from 2 to 3 for some of them. The electrons for some of them jumped 2 to 4. Some of them jumped 2 to 5, 2 to 6, and 2 to 7. So hydrogen has these allowed set of levels, and therefore a certain set of colors that correspond to photons that are related to the allowed levels. Remember, color is the energy that the photon carries. So red photons have low energy, violet photons have high energy. A higher energy jump from 2 to 7 requires a violet photon. A lower energy jump from 2 to 3 requires a red photon. So hydrogen will always produce this set of dark lines because of the allowed levels that the electron can jump to and the electron can jump from. Now let's do the other case. So what about an emission line spectrum? Well, what I want you to notice this time is the scenario is almost the same, but notice how the incandescent light bulb is missing. If you remember Kirchhoff's laws from a previous segment, Kirchhoff's law for an emission line spectrum says that you must have a hot, transparent cloud of gas where the cloud is the source of the light. So this hydrogen cloud is hot and it is giving off the light. So there's no need for an incandescent light bulb. Now what I want you to notice is this electron is in a particular orbital level, and what's going to happen is the electron is going to make a jump. And when the electron jumps from one level to a lower level, remember it has to give up energy to go from a high level to a lower level. So when the electron jumps from a higher level to a lower level, it will give up energy to make the jump down to a low energy level. But in the process of giving up the energy, it does so by giving up a photon. So this electron that's going around the nucleus in level 3 is going to jump down to level 2, and it will give up a photon. Now, why is the photon that it gives up the same exact shade of red that we saw previously? Because the energy difference between level 2 and level 3 requires the same amount of energy whether you go from a low to a higher level or a higher level to a lower level. So the shade of red that the electron takes in to make a jump up has to be the exact same shade of red that the electron gives off to make the jump downward. So when the electron jumps downward, it gives off this particular photon, and so what will happen is we will only see that shade of red. So this shade of red that we see against a dark background is because some of the atoms are making the jump from 3 to 2, some of the other atoms in the cloud are making the jump from 4 to 2, and then 5 to 2, 6 to 2, and 7 to 2. And so you'll notice there is no incandescent light bulb to produce any colorful background colors. So what we end up getting is the jumps from a higher energy level to a lower energy level to create the colorful lines. But because it's the exact same jumps from one level to another or from that level back to the first, it is always the same colors that are emitted as the colors that are absorbed. So in this example, we end up having the energy levels change, but for hydrogen, the red corresponds to the same jump as before, but now the electron gives up its energy as a photon, and then it comes down from level 3 to level 2. And so what we end up getting is essentially two patterns. If this is the element hydrogen producing an absorption line spectrum, this is the element hydrogen producing an emission line spectrum. The colors that are missing happen to be the colors that are present because it's the same orbit levels. This is just simply electrons jumping from one level to a higher level, and this is atoms where the electrons are dropping from a higher level to a lower level, but it has to be the same energy differences because it's the same levels that it's allowed to have its electrons in. So the pattern can be dark background, bright colors, or bright background, dark colors. You're going to get the exact same pattern. And as we said in the previous segment, because every single element on the periodic table has a different number of protons in the nucleus and will consequently have a different set of energy levels, what we end up getting is a completely unique pattern of lines for every element on the periodic table, because no two atoms have the same allowed energy levels, and so the pattern for every single element is going to be unique to that element. Now, one last thing I want to show you is how do we do this in the real world? Well, when you go to a telescope and you take a photograph of the spectrum of a star, it might look something like you see here. So notice this is an absorption line spectrum, colorful background, and various dark lines. But in astronomy, we're not so interested in the pretty picture. What we want to know is the information that this picture contains. For instance, there's two things we need to know. The first thing is, what is the exact color that is missing? Remember, color is wavelength. So we need to know what is the wavelength of every one of these dark lines. The second thing we want to know is, you'll notice how some lines are very dark, but some are not as dark. So we need to know just how dark is each of these lines. So the way that we do this is we don't use the pretty picture. What we actually do is we graph what the picture is trying to show. So this picture turns into this graph. And everywhere there's a dark line, you end up getting a dip in the graph. So if you look very carefully, you'll notice that this vertical axis right here is intensity. Intensity means how much is the color in its brightness. So you have a very bright shade of one color or a very faint shade of another color. The horizontal axis is wavelength. Remember, wavelength is color. So when we start at 7,000, we start in the red, and we go down to 6,000 angstroms, 5,000 angstroms, all the way to 3,000 angstroms. We're going from red all the way to the violet. Notice how where you have lots of color, you have this line that goes up. Notice the line that I've drawn on the screen here. So you have lots of color in the background. But what you'll notice is that everywhere you have a dark line, you have that color gone. And so the line essentially drops and dips downward everywhere there's a line. So when an astronomer looks at this graph, they know to interpret this graph to be something like this picture. This is a colorful background, an absorption line. Colorful background, absorption line. colorful background, absorption line. And this superimposed line that you see here, of course, this is what we referred to in a previous segment as a blackbody curve. So what I'm going to do is show you just a couple of very quick examples, because we're getting short on time, but I've got time for a few. Here is an actual graph of an absorption line spectrum. So this is the spectrum of a star. Notice that it has a very bright, colorful background, but every now and then you have certain colors missing. And so this is what the reality of it, what it looks like, and this is what an astronomer spends his or her time studying. So we're just about out of time. I hope you'll join me next time.